Okay, hello, welcome to AMAT 100. My name is Eli Bashringer, and I'll be your instructor for this course, which is pre-calculus. So this is going to be one of many pre-recorded lectures. There should be, unless I say otherwise, there should be one each week. And I apologize for getting this out a little bit later than I wanted to. I was having difficulties with the internet, and in fact, I'm still having difficulties with the internet, so hopefully it doesn't cut out on me. And also trying to figure out how exactly I'm going to do this pre-recorded lecture, because this is my first time doing this. Last semester I taught, I just had extended office hours, and I didn't do anything like this. But now they want all the pre-calculus teachers to do this. So let's just get right into it. We're gonna in this lecture we're gonna cover sections 1.1 and 1.2, and so it should be fairly quick. These are fairly easy sections, and actually you should have already been able to start the homework. It's fairly straightforward, but if you haven't, that's all right. I might actually extend the homework a little bit more than I have already done, because I'm getting this lecture out late. All right, so let me share my screen. Screen one, okay. So let's pull up OneNote. Okay, so section 1.1 is on real numbers and various subsets that we'll be dealing with. So this is probably actually the harder of the two sections that I'm going to cover today, because it's going to deal with something perhaps you haven't seen yet, which is the notion of a set. Although it's fairly straightforward, it's still something new and might be a little confusing. So we're only going to be able to deal with real numbers in this course, no complex numbers or anything like that, and various subsets, as I said. So the first collection of numbers I want to introduce you to is the natural numbers. So we denote this by n, and these are just the counting numbers essentially. So it's 1, 2, 3, 4, etc. So this notation right here, you have these curly brackets right here. This is the set, and then anything between it are the elements of the set. And then we also have integers, which are essentially an extension of the naturals. This consists of the natural numbers, 0, and the negative and negatives of the natural numbers. So we have -3, -2, -1, 0, 1, 2, 3, etc. And the ellipses indicate that this sequence just keeps going on. So as you can see, I mean, there's a lot of technical, I mean, it doesn't seem like it's technical jargon at first, but there is notions that we'll be discussing that do have some technicalities to it, but they're intuitive in some sense as well. And that is namely subset. So it's clear that n is a subset of z, because every element in n is also in z. And we're going to kind of build on from the naturals, from the integers to the rationals, which are the fractions essentially, to the real numbers. And before I introduce the rational numbers, though, I want to talk about sets a little bit more. So we have just some notation, and it's just formalizing everything we kind of can already know about sets, the intuitive properties of sets. So first of all, if A is a set, so capital A, and X an element in A, we let this string of symbols right here, X, this epsilon or E looking thing, and A, mean X is in A, or X is an element of A. So these are just two ways of saying the same thing. And this is just shorthand. This right here is just shorthand for saying that X is in A, or X is an element A, or X is a member or an object in our set A. So that's just one formalization or symbolization of something intuitive that we already know. And then we also want to talk about what's called the so-called set builder notation. I don't really understand the terminology behind it, but if A is a set, it consists of things, and the idea is that there's a condition or a condition its elements must satisfy in order to be in the set. So you have this set of, well, just let's say I don't know, a set of red things. So you collect all things that are red and put them in there, and they are in that set by virtue of being red. They satisfy this condition or property. And so we want to be able to express that in a short way that will enable us to define more complicated sets. So we have this so-called set builder notation that allows us to do this. And this is just terminology, more terminology for something that's pretty intuitive and straightforward. So the idea is that A is some set, and it consists of things, and it consists of those things, and they satisfy some property that makes them a part of this set. So what we do is we say we just write it in this way, and I'll explain it after I write it. So this right here, this X is an element, just some element of A, some arbitrary element. And then this right here, this P of X, is maybe some statement about X. Is a statement or proposition or condition X must satisfy in order to be an element of A, set A. So for example, P of X could be the statement X is red. So it's this proposition, and then you look at all the things in reality and you say, okay, is this red? It satisfies this condition, so you put it in the set. And then finally, this little bar here, sometimes they use colons. I just tend to use this bar. It's meant to be read as such that. So this right here, this is an equation, and it's a sentence. It's saying something. What it says is that A equals or is the set of all X such that P of X is true. Or for example, A is the set of all X such that X is red. So this is just a neat way or a concise way of describing a set. Instead of using all this natural language, we just formalize it into mathematical language. So with that in mind, we can now define the set of rational numbers. So the rational numbers are denoted as Q, and it consists of all elements of this form, P over Q fractions, such that P and Q are integers, and Q is not 0. So in this case, in the first case, in the definition, it's not really a definition. I presented a simplified version of what a set is, or the set builder notation, because I only had one variable x, and then the proposition was is like a function, or depends upon just this one variable. But you can, as you can see in the case of the rational numbers, you can have any number of parameters or variables you want. So in this case, we have P and Q. In order for P and Q, P over Q, or this fraction, to be an element in Q, first of all, P and Q have to be integers, and Q has to be non-zero. You can't have division by 0. So this is just a concise way of defining the rational numbers. So, and then finally, the R really can't be defined, which is sort of weird. So R is the set of all real numbers. Without some really, really advanced mathematics, you can't really define R. It's a set of all real numbers. So it's like the union. It's like you take all, so you take all Q, and then you take, well, I didn't define this notation right here, this U right here, but it's Q union with all irrational numbers. This isn't really a whole lot accurate because I haven't even really defined what an irrational number is, but we kind of have an idea of what these are. These are like pi, say, or square root of 2. An irrational number is just any number that isn't rational. They can't be expressed as a fraction or a repeating decimal. So these are the primary sets we're going to be, the main sets we're going to be dealing with. And then really R is the main set we're going to be dealing with. And then we're going to be dealing with these various subsets, N, Z, and Q. And then there will be another set I'll introduce. But first I want to talk about so-called operations on sets. Sorry about that. I got 4 dogs. They're just going crazy, I guess. So, so we have operations on sets. So in some sense, sets are a lot like numbers in a way. In the case of numbers, you have addition. You can multiply sets. You can add and multiply sets, really. I mean, I'm sorry, in the case of numbers, you can add numbers and you can multiply numbers, etc. And you can do something similar with sets. You have a way of adding and multiplying. You have this arithmetic of sets. And so the first way is something that's kind of, in some sense, adding sets. I'll put this right here, adding sets in parentheses. So if A and B are sets, we can define their union is a new set built from A and B. And it's probably just what you would imagine it to be. You just take everything in A and everything in B, and you just put it all together. But we can express that more concisely and more concisely and precisely as this. So A union B, so this is right here, A union B, and we're defining it. And sometimes you'll see, maybe especially if you do computer science, you'll see people use this notation a lot. I'm rather partial to it myself. You use this colon equal sign, and that just means define. These symbols right here are just, they're empty symbols. They have no meaning. And now I'm assigning meaning to them. So I'm saying I'm going to build this new set, A union B, from given sets A and B. And it's going to consist of all X such that X is in A, or, this is important, X is in B. So as I said, this is kind of like addition of sets. And the number, so the number 0 in real numbers plays the role of, or well, it functions in such a way that when you add it to any other number, you just get that number back. So you have A plus 0 is equal to 0, A, which is equal to 0 plus A. So it just does nothing to it. And in some sense, we have this other set, which we're going to call the empty set. So equals empty set. This plays the role of 0. And so as you can gather, the empty set is the set consisting of nothing, which is kind of weird when you think about it, but 0 itself is a rather weird number. But if you take A union A, you just get A, right? So it's like you added nothing. It's like this is, in some sense, union really just is adding, it's like the addition or plussing two sets together, and the empty set plays the role of 0. And then, so now we're going to do something like multiplying two sets. So again, we have A and B are sets, and we talk about the intersection of A and B is the new set. A intersect B, and we define it to be consist of all the X such that X is in A and X is in B. And so A and B can be really any set, but let's just imagine that just for now, we're just taking everything to be subset. So here's another symbol notation I didn't introduce. Let me not be too, might be too confusing. Hold on. So we have, let's see. So this symbol right here means something like included in or a subset of. So this just means A is a subset of R, and we're taking B to be a subset of R. So somehow like R is the universal set. And it's like it's containing all of our other sets. And if that's the case, then R plays the role of the number 1 in multiplication. Why? Why? Well, if you do A intersect R, it's not hard to see that it's just equal to A, which is the same thing as R intersect A. And that's exactly what we have with numbers. If I do 1 times A, it's equal to A, which is equal to A times 1. If you multiply 1 by any number, you just get the number back. So in this sense, R is playing the role of 1. So union is like addition, and intersection is some sense like multiplication. So the last set I want to introduce is are these intervals. So we have these are like continuums. They're like, it's like a line, it's a subset of R that's like a segment of it. So let's see, so we have two basic ones. There are a lot of variants on it, and I'll pull this page up, but we have the open set. And this notion of open is really important when you get into more advanced mathematics in this branch of math called topology, where you think about like space and how you can deform it and stretch it. And it has a huge role in, as you can guess, it has a huge role in, say, like physics, like general relativity. And it just shows up everywhere. Topology is a very fundamental branch of mathematics. So this idea of an open set is very important. But you have this open set, and this is how you define it. So if you take two numbers, A and B, so these are in R, so A is less than B, they're real numbers, then this parenthesis A comma B parenthesis is defined to be the set of all x such that x is greater than A but less than B, is the open interval from A to B. And if you want to just graph that, has a pretty easy picture. So there's a pretty easy way of visualizing it. So if you have A and B over here, notice that A and B themselves are not in the set, right? Because A can't be greater than itself, right? And likewise, B can't be less than itself. So the way you denote this, usually, there's a couple ways to denote it, is you put a circle here at A and a circle here, open circle at B, to denote that like you're plucking those points out. You don't want those in the set, but it consists of everything in here. So everything between A and B. On the other hand, there's this other set called the closed set. Again, a very fundamental set in topology. It's the closed set, and it consists of all the x. I guess you could say all x, yeah, real numbers x, such that A is less than or equal to x, and x is less than or equal to B. And this is called the closed interval, or just the closed interval, from A to B. And then the only difference between, so yeah, we can just graph this again. It's not that hard. So we have A here, B here, so A, B, and then you just put a solid circle here and a solid circle here to denote the fact that A and B are in there. And they really are, because A is less than or equal to itself, right? It's actually just equal to itself. A is equal to A. So it satisfies the condition of being in that set. So I guess maybe I should do example. Yeah, let's do some examples. Actually, I haven't done any examples. So since this is fresh in mind, let's look at the set -1 and 1 is 0 inside -1 to 1. Well, let's go to the definition. It's 0 is in. And remember, in order to be in this set, in order for an element to be in a set, it has to satisfy the condition for membership to be in this set. Well, what's that condition? Well, in this case, we're taking A to be -1, B to be 1. So we can just write out the definition of the set, right? So it's all the x such that x is greater than -1, it's less than 1. Well, this is certainly true, right? 0 is greater than -1, and it's less than 1. So that implies that 0 is a part of that set. Okay. And so there's a little example here. Let's do something with, how long have I been recording? I don't even know. Let's do something with the unions and intersections. So suppose we have this set, -1, 0, 2, and then we have, let's say, 1, no, let's say -3, 0, 1. So A union B, remember, it's everything in A and everything in B. You take both things and put them together. So this will consist of -3, -1, 0, 1, and 2. Notice there's no repeats. That's something I forgot to mention. There's no in a set. It's an unordered list. The order doesn't matter. Well, okay. No, I'm sorry. The point is that we don't repeats are we don't put repeats in the set. And I forgot to mention that. I'm sorry. So that's A union B. Let's look at A intersect B. Well, we have to look at what's in common. So over here we have -1. Is -1 over in? Is it -1 in B? No. So that doesn't belong to the set. What about 0? Yes, 0 is in both A and B, so we include 0. What about 2? Is 2 in here? No. So 2 is not in B, and then you can go through B. You can ask yourself, okay, is -3 in A? No. 0 is in A. Is in 1 in A? No. So the only set elements that A intersect B will consist of is 0. So those are some examples. Let me pull up. Hopefully this is working. I'm looking at the textbook now. So we looked at open sets. We have this is the open set right here. This is the closed set right here. And we have variants. And the symbols that you use should pretty well indicate how the set is defined. Usually like this open, the parentheses means that you don't include the endpoints, and the square brackets means you include the endpoints. So for instance, this third one is square bracket A, comma B, parenthesis. And how you define that is it's all the x such that A is less than or equal to x, but it's strictly less than B. And then over here we have this graphical representation of the sets. So I'm not going to go through all of them, but I encourage you to look at them. And then, yeah, maybe we should do this example right here. So we have, we want to find the union. This gets a little more tricky. Unions and intersections of intervals. So let's go through this. So we have two examples. These come from the book. They're example 6 in section 1.1. So we have example number 6. So the first one is A. We want to graph 1, 3 intersect 2, 7. So for intersections, what I like to do, we want to find the overlap between these two sets. And what I like to do is I like to draw 2 copies of the real line and place them parallel like so. And then I'm going to plot. So we have 2 sets and we're intersecting them. And I want to, I'm going to put one set on each line. So maybe we have, let's say 0 is here. This is 1. This is 2, 3, 4, 5, 6, and then finally 7. So I'm going to call this, I'm going to graph, I'm going to call this A, and then I'm going to call this B. So this will, on the first line, I'm going to graph A, and then the second line, I'll graph B. So A is everything from 1 to 3. So I'm going to put an open circle at oops, I'm going to put an open circle at 1 because we don't, the parenthesis indicates that we don't include the endpoint. And I'm going to put an open circle at 3. And then we're everything between there. And then for B, it's everything from 2, so solid circle at 2, and then a solid circle at 7. And that's everything between there. And then the idea is I want to look at what's overlapping. So we have this overlap here, and then partial overlap here. So this should tell me how to graph these two. So the only thing you have to be really careful about is, do I include endpoints or don't I? Do I include endpoints in the intersection or don't I? So 2 is in B, and it's also in set A because it's between the endpoints. So I'm definitely going to include 2. So I'm not going to be too careful about matching up these lines. So we're going to have 2 right here. Now, somewhere over here, we're going to have 3. So it's clear that everything between 2 and 3 is definitely in there. But what about 3? Well, 3 is definitely in B because it's between 2 and 7. But 3 is not an element of A. It's an excluded endpoint. So we're not going to include it. We're going to put a solid circle. So it's the intersection will be from 2, including 2, up to 3, but not including it. And so what that means is that, so this is a graphical representation of it, but we can also, from this graphical representation, we can deduce what the actual set's going to be. So it's going to be, the intersection will be from of 1 to 3 to 2 to 7. It's going to be the set 2 to 3, but not including it. So it's square bracket because we include 3, but parenthesis because we don't include 3. So that's one example right there. The union is not too bad. I'll just leave that up to you. This is example 6. So this is part A. Yeah, I did part A. If you want to go through part B, maybe that's something we'll do on Friday. I don't know. I haven't figured out exactly what I'm going to do on Friday. It's mostly going to just be review. I'm going to leave it open to you. Like if you have questions about this lecture, we can go over those, or if you have questions about the text when you're reading it. And then if there's no questions, we'll just do a couple examples and then call it a day. So let's see. So the last thing I want to do in section 1.1 is absolute value. And it's pretty straightforward. So the absolute value so if A is a real number, the absolute value of A is defined to be, so this is the absolute value, these vertical lines enclosing A, and I'm telling you what it means. I'm giving you a definition. It's either A, this is a multi-part definition. So the absolute value of A is equal to A if A is greater than or equal to 0, or it's equal to negative A if A is less than or equal to 0. So immediately from this, we can see that the absolute value of A is always positive. It's always non-negative because it can be 0. So it should be clear from that. You can go through the definition. It's pretty clear from the definition that that's the case. And what it represents, the distance of A from 0, the origin so 0 is our like distinguished point. It's the origin of R, the real line. And from this, we can just define a distance. We get a so-called distance function. Or actually, let me list these properties right here first. So one I already stated. And these can be easily proven. I can leave that up to you maybe, or maybe we'll go over them. I don't know. So we have that the absolute value of A is greater than or equal to 0. The absolute value of A is equal to the absolute value of negative A. So in other words, like the absolute value just can't tell the difference between A and negative A. And that makes sense because we want absolute value to be distance from origin. And A and negative A are at the same distance to the origin. They're just on opposite sides of 0. The third property says that you can distribute, in some sense, distribute the absolute value over products. And 4 says you can distribute, in some sense, this is all with like question mark or quotation marks because this is like approximately what it's saying. But it says that the absolute value roughly distributes over fractions. And then the last one is the so-called triangle inequality, which is best illustrated in 2 dimensions. So let me just write down what this is saying. So the absolute value or the triangle inequality says this. It says that the absolute value A plus B is less than or equal to absolute value of A plus absolute value of B. And if we're instead thinking about points in the plane rather than on a straight line, this makes more sense. It says roughly like if you have a point A here, and then you have point B here, this is supposed to be a straight line. It says that this length right here is less than if you go this way and then this way. Oh, sorry, hold on. No. Wait, I'm screwing this up here, actually. Yeah, no, this is right. So B is up here. So A is down here. And then B is up in this corner. And this hypotenuse, this what's this called? Hypotenuse. The length of this is less than the length of the sum of the sides. So it's, in other words, it takes, you travel less going along the straight line. That's all that triangle inequality is saying. Let's see. One last thing from this section I want to mention is this distance function. So if you have 2 points, A and B, on the real line, their distance apart is just this, which of course is actually the same thing as just doing this. You can switch them around like that. And I'll leave it to you to think about why you can do that. And it has to do with property 2 here. The fact that absolute value A minus B is the same as the absolute value of B minus A follows from property 2. So that's section 1.1. Let's move on to 1.2, and then that'll be all. So let me see something. Am I recording actually? Yeah, I'm recording. Let me share my screen again. So let's see, I got section 1.2 is on exponents and radicals. I'm not going to spend a whole lot time on this because this is pretty straightforward stuff. I want to spend more time on the notion of a set, just because that's probably something you haven't really seen before. So let me just go through these definitions really quick. So we have exponential notation. And as always in math, none of this crazy notation is meant to confuse. It's just to simplify things and put things in a more convenient form. So if A is a real number and n is a positive integer, so it's a natural number, in other words, then we define a to the n to be equal to a times a times a. And this is n, you have n factors of a, all right? You're multiplying a by itself n times. So this is what the meaning of this notation is. And of course we've seen it, I'm sure we've all seen it, but you know, we're in college level math now, so we have to be more careful about what's a definition and what's an axiom, basically. This is a definition. So a is called the base. And n is called the exponent. There's these simple examples. I'm not going to go through them. If you really want, we can go through. Whoops. If you really want, we can go through them tomorrow. But I want to try to keep this short. I feel like it's pretty long as it is, this lecture. So that's just the definition. And then just an observation, a easy observation. A to the n times a to the m is just the same, is the same as a to the n plus m. And sorry, I'm working with two monitors here, so it's a little confusing. So now if a is non-zero, it's a non-zero real number, then a to the 0, so we know what a to the n is for when n is a positive integer, natural number, 1, 2, 3, or 4, 5. But now we need to set up some conventions. So we just define a to the 0 to be 1, and a to the negative n, sorry, I should say here, n is a natural number, a to the negative n, so to be 1 over a to the n. So we're kind of extending these the definitions that I just gave. So before I gave this definition, we didn't know what to do with a to the negative power. But now we do. We just say you just take the reciprocal of a to the n. So this gives a way of computing that. And then let me share this part of this book. This is section 1.2, laws of exponents. This is one I already mentioned. This follows, number 2 follows from the definition I just gave, which is right here, actually. You can deduce this right here. This is not hard. Then you have powers of powers. You just multiply them. If you have a product raised to a power, you just kind of, in some sense, distribute the power. The same holds for fractions. If you have a fraction raised to the power, you just, in some sense, distribute the power. And then these also are pretty straightforward. So let's see what else is in this section. So Yeah, I guess I'll go now. I'll say these examples for tomorrow, actually. Okay, so the last thing I want to talk about are radicals. So if n is a positive integer or natural number, then the principal and through, so principal and through of A is defined to be this. And this means b to the n is equal to A. So this doesn't have a meaning until I assign it meaning, and I'm telling you what it means. And if n is even, we have to insist that A and B are positive, or non-negative, I should say. So in other words, this nth root of A is that number such that when you raise it to n, you get A back. So in some sense, like radicals and exponentiation, so at roots and nth roots, or nth powers and nth roots are in some sense dual or opposite of each other. This just simply means the nth root of A is that number such that when you raise it to the nth power, you recover A, you get A back. And that's all that this sentence is saying right here. And there's some examples, but as I said, I think I'll just go over those tomorrow. And let me just maybe show you this, the properties of, yeah, we got properties and then, okay, yeah, let's show you this properties. Let me show you this, oops. Let me show you the properties first. So this is assuming, you have to be careful about whether A or B is positive, and actually they don't really state it here. But the nth root of a product is the product of the nth roots. So this nth root in some sense distributes over the product. And then the same thing with ratios or fractions. The nth root of a fraction is the fraction of the nth roots that distributes in that sense. And then you have this mth root of the nth root just becomes the mnth root, m times nth root. And here's where you have to be careful about whether n is even or odd, or what A is positive or negative. So if n is odd, then when you take the nth root of n, you get A back. And that's exactly what I was saying in this definition right here, up here. It says that if the nth root of A is that number, when you raise it to the nth power, you get A back. So that's exactly what this is saying right here. And but in the case that n is even, you have to be careful because you don't want, like for instance, you don't want the square root of a negative number. The square root is the as a second root. It's n is and will be even. So you don't want say the square root of -1, because we're dealing with real numbers only. And the square root of -1 is not a real number, I should point out. So let's see. We'll just do one last definition, and then for this section, I'll go over examples tomorrow. So the last definition is for rational exponents. So again, we're just like doing this in some sense, like piecewise or inductively. Like we start with some really basic stuff and then we're building on it. So we know how to take integer exponents. Well, how do we do rational exponents? Now we just extend that definition. So if you take a fraction, m over n, in lowest form, so for example, that would be 1/2, but not 2/4. So 1/2 is in lowest form, but 2/4 is not, because it has the numerator and denominator common factor. So if m over n is in lowest form, and m and n are integers, obviously, but also n is positive, then we can define these rational exponents. And so this is a definition. So this means the following. It's the nth root of a raised to the nth power. Or equivalently, you can write that as saying it's the same thing as saying this. And if again, we have to worry about square roots of negative numbers. So if n is even, then we insist that a has to be positive. Otherwise, this definition doesn't make sense because we get imaginary numbers. So that's all I want to go over for now. For this section, this is really where I'm going to do some examples. I'll do examples of section 1.1 tomorrow also, but I want to do some examples more so from 1.2. So this is all for now, and I will see you tomorrow. So let me stop sharing and